Okay, let others come. Am I audible to everybody? Let us start. Hello? Am I audible to everybody?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Now, today at the afternoon, we had classes for solid mechanics laboratories. For this, to start this lab, I will narrate the experiments of strength of material laboratories because both all of them are required and we should remember all the details to know the solid mechanics labs experiments. Today I will start with torsion test first. I have the video. I have video as well as the layout. I mean this operation manual. I'll discuss and and ask you about some questions over it. Let us see. Now, we have several videos in torsion test lab, torsion test machine. This is the machine has two vices. This is one of the vice to which our workpiece or test piece is being fixed by means of these two tables itself. This vice has a graduated scale which records the degree of rotation during the torsion test itself. And this is the indicator angle which will show you the amount the degree where the torsion will take place, where the breakage will take place. This is a digital load display which will display the load, and by pressing the peak switch, we load at the point of breaking will be displayed and remains there without going back to the zero switch. This is the main switch, and this will glow with the peak switch which applicable itself. Now, this I've just told you. This is one of the graduated scale, which gives us the graduation of 0 to 360 degree, and it will rotate. And at the moment of breakage, the reading given by this thing will be the amount of rotation the torsion test. I mean the workpiece twisted before breakage. Sometimes it happens three or more complete twist is required to break it. Here is the motor itself, and this is a gear gear driven wheel which runs this runs this device, which is the one side holder of the torsion testing bar itself. Stop share. I've given you another thing. Uh, Here we have this our workpiece, which is after it breaks, it shows the position, its position here, and here at around 110 degree, around 90 degree scale, the torsion that is broken over the situated bar itself here, and 4.49 is the breaking torque, which is displayed by the peak switch of the machine itself. And the peak switch operates the top highest load will indicate, and it will not go back after breaking itself. Let us show another one. Again, the same portion is being reviewed here, but it is fixed before the breakage of the bar itself. This is a one vice, and this is another vice between which the workpiece is being held by a pair of switch, a pair of screw for both the sides. Here, it is already shows some loading because we have to make it zero before the machine started, because due to the adjustment of the workpiece, there can some loading can be shown here. This is the switch itself, which when it moves left side, the machine starts operating. This is say the flywheel is moving, and the body starts, and the body start twisting, and the value of the tonnage is going up and up, and before it reaches a certain position, there after that the bar twists and twisted, but generally the load doesn't increase to that extent. Now it is shown that for each for few degrees of rotation, this is being increased, and the bar this circular graduated disc is also rotating, showing that degree is improving 210, 220 SR like this, and display here is going on increasing it. And at the moment of breakage, the tonnage required, the brake will kept here, as we have operating the peak switch, which will keep the loading at the peak remains as it is. Okay, let us go for the reading of the manual itself. Just 1 second. Take Now the operative instruction for running the torsion test itself. What is going on here, given here, when you have uh, gone through this operation, I hope everybody of you have seen it at the time of your third semester job. The operative machine's instruction is like this. The machine is designed, what is given is, what is the machine is made for? It is designed for conducting torsion and twist test on, say, on around flat and strips and tube specimens. What we have shown is a cylindrical specimen with two square dumbbell-shaped ends, which is required for holding the specimen on the worksheet itself. But the if required, you can have and flat workpiece or strips, or can be two specimens. But only one mandatory requirement is there. All the ends of all these specimens should be made square and should have dimension equal required for dimensions necessary for accommodating inside the vise itself. Because the holding of the workpiece on this vise on this type of machine is only on the tube, on the by inserting the matter a square workpiece inside the cavity of the vise and locate it and fix it by tightening the two bolts kept on the vise itself. Now, every sort of test by in ferrous or non-ferrous of any material or any other metal, even soft materials, we can make the torsion, make the torsion test, but only best only that because we have to make the work specimen according to the requirement and according to the length required. And length, maximum length is for when can have accommodate is around 1 feet, and thickness, although our specimen is not that big, and workspace is given as the round portion of the part itself. It is the length of the workpiece itself, not the uh, dumbbell shaped square ends. Now, actually, this torsion is torque is nothing. Torsion or torque is measured by an electronic torque transducers. Here, it transforms the torque by means of the transducer into a different amount of force required to make this type of twist. The torque is applied by a geared box, which I've just shown you through reduction gearbox assembly. Here, a flywheel is a flywheel is given by chain drive, which means there is no slippage in the flywheel, so that the machines can transfer the full power directly to the twist for the twist of the workpiece. You see, we have broken the workpiece during the at the end of the twist. So this is a destructive test. You cannot make any of your mother elements to any other elements to run on these testing machines because it will break the specimen or and rather make it useless. So what we have to do is what you have to do is you have to make the specimen with the material concerned, with the material and all the design parameters with which your material is being tested, and then you have to use this and break it. And the result found is on this by breaking this type of specimen is applicable to the original specimen itself. This is the process method we used universally for all these destructive testing machines itself. The construction machines, what we have seen is at the full foundation itself, a measuring panel living on the left side of the machine, if stand from front, which is a display device, and a driving unit coupled with the with a gearbox with a vice, and over a vice on the right side of the machine from front, over a vice from the right side of the machine from the front will it is a rotating scale. A round scale is fixed to it to the scale, so that which will give you the amount of rotation which is going on from 0 to 360 degree. And it may so happen the bar the our required work means say required several twists before breaking it so that it may so happen we have seen that 6 to 7 twist is full twist is required before breakage of the material itself. So you have to measure the amount of twist, say 6 times you have twisted, so you have to make 360 degree minus in multiplied by 6 is 1080 degree amount of degree rotation is required before the twisting itself. The measuring panel is, just I have told you, is electronic microprocessor based digital indicator unit. It with the its sensor is fixed inside the left face, when which sends the twists of the specimen twist and records the amount of torque, record the amount converted into torque and showed in the showed in this digital indicator unit itself. A driving unit, a geared motor is fitted on the reduction gearbox housing. A motor is there. Motor is being run from a through the gearbox, which is kept on the right side of the machine itself. A drive from the motor is given to this worm shaft through a chain sprocket drive. This worm and worm shaft are being supported by the in the gearbox housing itself. The trolley is supported on this four ball bearing. A trolley supported on the four bearing travels over the base of the frame, paid for adjusting the length of this specimen. What we have shown you on the right side of the machine, a motor, a gearbox, a chain sprocket, uh, a chain operated machine, chain driven vice, which are all together is housed in a rigid body on the right side. But this body can move from over the rail of the machine from right to left up to a certain distance, so that to accommodate the length of the workpiece itself. And the digital indicator displays the torque in bright digital display. You see, at the time of discussion of Young's Hooke's law, we told that Hooke's law is stress is proportional to strain, provided only when this obeys up to this works within the elastic limit. But you see, in all these strength of material experiments, we make a destructive test, either impinging a hard indenter into a body or rotating and breaking a workpiece by tensile tests is pulling and breaking their workspace like this. These are all destructive tests, but still we are using the result of this test with the idea that we have seen that the result of this test are applicable to the applicable to our practical purposes to a simple but acceptable accuracy itself. Now let us discuss the theory behind the torsion test itself. A torsion test is quite instrumental in defining the value of the modulus of rigidity. The ratio of shear stress to shear strain is also another formation of Hooke's law. The modulus of rigidity is equal to ratio of shear stress to shear strain, where shear stress is the amount of torsional test or amount of torque supposed to be apply on the machine before it breaks, and shear strain is the amount of twist it is made during the uh, by the full rotation of the disc of the specimen before it breaks. This breaks that is the metal, which means which is milling here the metallic specimen itself. Acha, the value of the modulus rigidity can thou be found out by the observation made during the torsion equation. What is the torsion equation here? We have no when in third semester you have understood the torsion equation is given by torque T divided by IP is the polar moment of inertia, which is equal to C modulus of rigidity multiplied by the angle of twist in radians divided by the length of the length of the gauge length of the bar itself. The gauge length is actually we take the gauge length between the lengths of from one dumbbell to another dumbbell. So this is from the modulus of from this torsion equation what we got the modulus of rigidity of the particular working experience, because applied torque we are measuring in the display device IP, the polar moment of inertia is equal to pi d to the power 4 by 32, which can easily calculate, which is possible to calculate very easily by determining the diameter of the text piece itself. And theta is the angle of twist. It is being measured from the rotating scale. So with this all these things, with all these inputs, we can safely calculate the modulus of rigidity of the said workpiece itself. Now, the operation process description of the machine is gives us the same thing we have just narrated. The machine, the ends of the specimens are held in suitable grips or suitable vices, which I have shown you, through one of which is torque is applied. The left side of vice is fixed and doesn't rotate and houses the sensor for determining the torque applied to the workpiece itself. Right end is attached to a torque drum by means of which the torque of the specimen um, uh, actually left side of the heel is attached to the torque arm by means of which torque of the specimen is measured. Torque arm is attached to the indicating unit through intermediate gear leveler housing in the cabinet itself. The digital indicator is indicating the torque developed due to the twist of the specimen. So what we have here in the left side, we have the two vices for fixing the specimen. Left side of the housing, right side of the right side vice is used by applying the torque, and left side vice is attached to a torque arm by means of which the torque of the measurements is measured itself. The torque arm is attached to the indicating unit through intermediate leveler housed in the cabinet. The digital indicator is indicating the torque developed due to the twist of the test specimen itself. What is the operation procedure? Place the machine on a solid level surface. Provided the machine is always, all the machines are placed over a bed or foundation which is perfectly horizontal. And at the time of assembling or housing or mounting the machine on this device, we have to check by proper level indicator so that the machine is perfectly leveled to the horizontal floor. Now we have to supply 415 volts, three-phase 50 hertz AC current to the machine motor to run it from the mains. Now next we have to clamp the workpiece to the machine both the ends. Machine can be operated, right side of the vice can be operated both way, maybe clockwise, maybe anti-clockwise by just rotating the motor rotation, reversing the motor rotation, and this process is required sometimes to house this to the square end of the block inside the cavity itself. But except the amount of the except this length of the specimen which is housed inside the vice, other specimens are round and is to be tested. The shape of the specimen looks like a dumbbell itself. Now we have to measure the diameter of this workpiece in three different positions and take the average diameter which is required for measuring the polar moment of inertia IP. set the torque digital torque twister to zero position. After setting and fixing the twist, we have to set the digital display device to zero position by pressing the zero switch. And next we have to push the switch peak switch P, which will give you the peak load unchanged when it reaches the peak in the graduated scale in the display device. Set the round graduated scale to zero. There is the indicator point, indicator leveler, and you have to rotate the device by means of own hand, the graduated scale by means of own hand, so that it reaches the indicator point to the zero value of the indicator point itself. Now, electrical level control switch should be turned in reverse direction to active the driving charge. With this, the test specimen twist starts twists. With the increase in load, the display of the digital device progresses right rigidly on as well. Here, we run the machine in reverse direction, not in the forward direction, and rotate the by holding the grip between the brace. We just starts twisting the specimen quickly. Now we know the rotating graduated disc, the job in the forward direction and job will move in the forward direction takes the measurement of the torque after a definite interval. So after say 5 minutes or 10 minutes, we take an interval and see how for each degree of rotation, how much is the load on the load is being displaced over the display device itself. Now continue the procedure like this. Maybe twist maybe two, three, even so you have seen 7 twists for the block itself after it before it breaks. You continue the machine after it breaks, and after it breaks, then we have to with the result the torque and twist curve. So we have the result of for each say for 10 degree to 15-degree twist, how much the torque is being changed, and keep the result of the torque itself, and keep the result display of the torque itself. And if you have to poke a graph on the graph paper in ordinate system, there should be the number degree of twist, and on the I'm sorry, axis is the degree of twist, and the ordinate is the amount of torque created. Now read up the coordinates of the convenient point on the straight portion of the twist curve and calculate the value of C by using the relation. So you have to fix a convenient and consistent point upon the straight line portion of the toss twist, and you have to calculate the value of C by using the relation of angle of twist. So for a particular angle of for a mm, polar moment, to know the modulus of rigidity, the polar moment to calculate polar moment of inertia and everything. So we have to find out from the graph, we have to find a suitable line portion whose where the toss and twist curve is can be find out, and using this value of T value by C by using the relation itself. The what will be the torque here? The angle of twist in the radians, and the amount of torque will be given over placed over it, and you have to find the suitable angle of twist and torque, more or less when it is consistent or so. And you have to use this theta and t. This torque is t and theta is L in terms of radians, and you have to calculate IP, where you have already measured the diameter and 3 and 4 portion of the rod itself, and then get a then get a particular chap itself, then 2 3 portion, and then with the use average value of the D, you go the calculate what IP or polar moment of inertia itself. So angle of twist measured in degrees should be converted in radians before plotting the curve itself. Now, and with this torque and angle of twist, we got a curve and we got the value of C, and the value in the values of theta and torque you have displayed, or also in position in a different position of the curve itself. So machine will don't use it, then the power cord is have to remove from the mains itself. Okay, for the class, for today's practical, we have more or less finished by torsion phase test, and in the next class, we'll see what we are going to do over there. So till then, goodbye.